So, I was asking around the programming language Discord server about, I guess, like the utility of category theory. I don't know. I think there was a discussion going on. No, that's not right. There was an ongoing discussion for over the past week, and it eventually amounted to me being, well, yeah. So I asked about like category theory. What is it? Because like the way I view category theory is kind of like the theory of everything for maths. Like category theory is what we need. What we need. It's okay. We don't need it, but like it's a useful formal tool of declaring and finding patterns and abstractions. If that sounds like a lot of abstract nonsense, then I'm probably doing it right or explaining it right. So like, for example, if you have learned maths in school, you probably learned about oh, that's what it was. You probably learned about set theory, perhaps sets, right? Maybe you've learned about some. Would you learn about Boolean algebra actually? I don't know, but like sets, Boolean algebra, probability, relations maybe. These things have patterns between each other. There are things you can notice about each of them that relate to each other. But most teachers, the vast majority of teachers, don't bother teaching it, either because they themselves are not aware of it, although I find that hard to believe if they're a maths teacher. Generally, maths teachers are quite enthusiastic about maths, I feel. Or maybe not, I don't know. Or they think it would be too complicated, and not really worth the time. Maybe not, but I feel like if we're going to teach maths in school and make it a requirement, like, there are already loads of people calling to just remove it from the curriculum, because, like, what's the point, It's not going to be useful in most people's lives. But then they argue that, well, yeah, maths is useful because, it teaches you ways of thinking, like proofs, sort of like a whole, like, process of logic, and verification and patterns, finding patterns. In that case, how about instead of teaching set theory and, I don't know, relations and functions and graphs and, what's the other one? Probability. Like, sure, these are generally somewhat useful topics, like I might need to calculate the odds, or like make sure like I'm not getting scammed by like winning the lottery or whatever. Although we don't really even teach it in that context, so I don't really understand that. But at that point, why not just teach it the good, like, in the super useful way, which is the most general way? Like, maths in school isn't even taught to reflect maths like in like the real world, as in that mathematicians do like at a graduate level, Like, teach that, man. Like if category theory is truly the theory of everything abstract, right? The theory of everything abstract, then why not at least introduce it in school, Tell people, well, we have these things called a monoid, for example, with the integers, addition, it forms a monoid with a unit of 0, because if you add 1 plus 0, guess what? You get 1. But, this is familiar, right? Because it also applies to set theory. Now, if I take the union of an empty set and then some other random set, let's say it's just a set with a number 1, what do I get? I get the set of 1, the same thing. So, likewise, the unionization, or whatever the verb is, forms a monoid for sets under, or whatever, okay, whatever the terminology is. Point is, there's a monoid for sets with the units, for the union operation with the units of an empty set, right? And then you can say, and there's also a monoid for multiplication. That's right. Or think like, okay, class, what else? What other operation do we know in maths for numbers, for integers, right? That where you can do something but not get a difference. Like maybe Jimmy says, well, I can subtract 0, and you'll say, right, oh, yes, now subtraction. What is subtraction, guys? Like, what is it? Like, and then you can explain how, like, it's the opposite of addition, it's the inverse, we can learn what inverse means, which is, like, a general term in just in everyday life, to do the inverse of something, or the opposite. Well, the inverse specifically is to do the reverse, right? The inverse. If I load the dishwasher, then the inverse is unloading the dishwasher. Like, it's a general concept. And then You could want to explain, well, hold on, what is addition? And like, but then if I have integers and I subtract, then what is a negative number? It's a function? Wait, I'm composing functions when I do subtraction and addition? Addition's a function too? Are any numbers or are they all functions? What do you mean it's all functions? What's a morphism? And then you can go, like, that'd be so much more interesting, wouldn't it? So much more engaging and more useful, because then the reason that category theory is genuinely useful is because you can apply it to like a wide variety of fields. So like while like you're not learning something concrete per se, it makes learning things in the future a lot easier, and that's something that's really overlooked just in every aspect of life. You know, learning things makes learning other things easier. That's so overlooked. It's kind of insane. You know, and they can say, well, hold on, Miss or Mr. or whatever, teacher. If I multiply something by 1, it stays the same. And you say, what? Oh, yes, you're right. So, what does that mean? They say, well, if I use your words, that means that multiplication forms a monoid under, sorry, what? The integers form a monoid under multiplication with the units of 1. You say, yes, you're right. But let me ask you, class. Addition and multiplication, they're related, yes? Multiplication is kind of like repeated addition. What happens if I take the units of addition for the monoid, and then have that in multiplication? What happens? Oh, well, if I do 5 times 0, I get 0. And then you can say, yes, exactly. That is the, what's it called? The destruction thingy? No, yeah, that's right. That's right, class. We call that annihilation. Ugh. Like that's awesome, man. And then you can explain, and in fact, if I take these two things, I can get a semigroup. A semi-ring. What? What's a semi-ring? Well, a semi-ring is just that. I have 2 monoids, you know, where I have addition, or something like addition, and then something like multiplication. And you know which is which, because the multiplication, if I take the unit of addition and apply it to the multiplication thing, then I get annihilation. And they'll be like, oh, what? And you say, set theory, intersection, and unions form a semi-ring. And they'll say, what? No way. For Boolean algebra, that also forms a semi-ring. What? You know, and they can say, but wait, a semi-ring, like a semicircle. What's a circle? You say, whoa, you see. You know how Jimmy said earlier that subtraction is the inverse of addition? Well, there you go. A ring is just that. And then, like, kids will come out of school knowing category theory, something which most people look at and find really difficult to comprehend, you know? And like, I think that's that's kind of the sign that like something needs to change, which is that when I explain it like this, like it's pretty easy to grasp, right? But when most people look at category theory, they have no idea how to approach it. Like, it's so unfamiliar, but it shouldn't be, because it's just logic and abstraction, things that the human brain can already do. But if, you know, imagine if you were taught that as like a child, as like a 10-year-old child, maybe a bit after you learn like addition, like your times tables, whatever. But then like you really get into like the fun stuff, you know. Like, times tables are good to know to do like quick calculations, because, you know, even with phones, you don't have to pull out your calculator to calculate 8 times 12 or something, right? Like, it's genuinely useful to learn times tables, and I wish that times tables were also generally taught in a more like applied way for that reason. But once you get past the whole like, all right, this is how you count. You can do multiplication, okay? You can go back on the number line. You know, it's like going forward and walking backwards. You know, make it intuitive and make it like applied. Like these are things that are actually like essential to living every day. Because if you know how to do those things, you're kind of like you're gonna struggle. You know, or like converting percentage. You know, or like applying percentage. Like, I just divide by 100. It's like, yeah. It's like, oh, shit. It's like that. You know. So yeah, I'm just and then get into like the actual category theory stuff, you know? Like, still teach set theory, sure, and teach Boolean algebra, and teach probability, and teach relations and functions and graphs and all this kind of thing, but when you show that they're related, you know, it's not like, you know, like, then it's not like the students come into class and they're like, oh, we got a new topic, set theory. What is set theory? Venn diagram? I mean, it looks kind of cool, but like, what is this, bro? Like, every time they come into the maths class, they're learning something new. But like, you don't. Maths isn't created. It's discovered. So have them discover it by teaching them the tools they need to discover it. You know. When you start learning set theory, if you've, or well, rather, I guess you probably learn probability second. If you're gonna learn probability, like, take what you learned from set theory and apply it. If you learn set theory, take what you learned from basic arithmetic. Every child knows how to add and multiply. Guess what? You can add and multiply sets. You can add and multiply booleans. You know. Yeah, it's crazy. So like, no, don't teach programming in school, because programming languages are fallible, you know, like they can change, they can whatever, you know. Teach the things you need to know to learn programming. And that is really category theory, because that's what we apply to programming. Why? Because it gives us tools of abstraction and like patterns that we can apply to make programs more easily, that feel more intuitive. Boom. So, man, people are sleeping on category theory. Like, even talking to people who do know about category theory, and like, well, I say about people who know category theory, like quite a lot about it. Even they are, and like, they have confessed to liking maths, like liking maths for like the sake of maths. But like, even a lot of them are like, yeah, but like category theory isn't it isn't really useful, is it? And it's like, well, no, it is useful, because it's how we think. It's literally, well, okay, it's how we think. It makes thinking a lot easier. And that's what it's all about. You know, humans create tools, not just physical tools, but tools in the mind. So that's my rant. Anyway, the other thing that I got from that conversation, or whole whatever, is not this butterbeans recipe, but rather a bunch of resources. So this is categories for the lazy functional programmer. It's, well, these are lecture notes, but like it's a whole like thingy, right? I guess this is actually quite short, isn't it? Yeah, this is actually surprisingly short. So I could probably read through this quite fairly quickly. And this is the University of Nottingham. So shout out Nottingham. Are you Notting Hill or Nottingham? Not English. There's this website, NCATLab. People don't like it, but I mean, dude, like, but like, you know, I mean, it's like, okay. By the way, this is like a wiki for maths. So it's like Wikipedia for maths. Because I find that Wikipedia, the explanations kind of like, in fact, they don't kinda. They have said that they are written kind of for people who already know what the thing is about. And it's more of like a reminder, which I think is so shit. Like, can we have Wikipedia that actually, or like something like Wikipedia that actually teaches you? You know, people, like, I'm sick of reading things that are written for people who already know the thing. You know? Like, if I know the thing, I don't really need a reminder from Wikipedia. So who is Wikipedia actually for? This is a lot more useful, because I find that it actually explains what things are, at least to an extent. Now, how useful is it really? I don't know. And like, I gave a quick read of like this, and honestly, although a lot of it is like jargon that I don't understand, first of all, there are links that I can follow, and second of all, it's still fairly not too crazy to understand. Does that mean I'm gonna read this now? Probably not. But if I need a reference for something, I think I'm gonna look at this website instead of Wikipedia. But I mean, look at this, right? If C and D are enriched categories over a cosmos V, that is, a complete and co-complete symmetric closed model category, of course, then a profunctor F from C to D, that is, a V functor, D opposites with the products C to V, induces two adjoint V functors, F star, which is of V's complement opposite, the opposite of V's complement, to the opposites of D, or no, V raised to the opposite of D, and F up star, V D up to V C up. Abstractly, one V functor is given by currying to get a V functor, C to V D up, and then using the universal property of the free completion. And the other V functor is given by currying to get a V functor, D up to VC, taking opposites to get a V functor, D to VC up, and then using the universal property of free co-completion, we then have an adjunction, right? This beautiful equation. Now, what the fuck? But, yeah, actually, there's no but. I mean, that's just kind of ridiculous. But you know, maybe it's useful. I don't know. I mean, I see nucleus, I think atoms, and now I'm intrigued. Because I want to get into like the atoms of thought, you know? Anyway, so I sort of this thing. This is a book, Basic Category Theory by Tom Leinster from the University of Edinburgh. It was actually written in 2025. Or at least this was published in 2025. Okay, no, it's 2014, my bad. But this particular thing is dated 2025 for some reason. But here's a book on, well, I guess category theory, right? On basic category theory. And it's not even that long. Like, these are all the chapters. Like, compare that to category theory for programmers, which if I can pull up right, no, I have it on my, well, yeah, I have it locally, but I'll pull it up here as well. This has 500 pages. So first of all, 500 pages. This one is only 200 about. And this is like, well, part 1, bunch of chapters, part 2, bunch of chapters. Holy moly, it just keeps going. I thought there were 3 parts. Yeah, there are 3 parts. Part 3. And that's 473 pages, officially. You know? Whereas this one is officially 157. So, that's pretty cool, right? And apparently, programming language, category theory for programmers is quite hand-wavy, is what people have told me. And by people, I mean like multiple people have said this. Or maybe it's the same person each time and I just keep forgetting who they are. But I believe people do generally not champion this book necessarily. So I'm probably going to stop reading this book right about now. I got to chapter 6, and I was about to get to chapter 7. But like, I think given this book is so much shorter, and it's kind of like, also like, I like the formal definitions. Like, it's useful to look at it through a lens of programming to get like an intuition for it. But I feel like category theory for programmers leaves the actual formal stuff until much later, you know, with like the actual like notation, like in some cases even like the keywords aren't actually given until much later, which I know like can be good for easing some people, but for me, like, I want to just know the formal stuff so that I can keep it in my mind, because like if I see the formal stuff, I know like that's what it is, you know, so that I can use that to verify my own thinking. And again, like, this book is just so much shorter for some reason, so I think it'll be pretty good. Like, I mean, this goes into functors on page 17. This book goes into functors as a chapter in page 89, so it's quite a bit later. Yeah, and then we go adjoints, interludes, and sets. So it actually brings up sets later, which is probably a good thing, to be fair. Representables, I don't know what that is. Limits, I've heard of colimits, I don't know what those actually are. Assuming that it's not calculus. And then all that kind of stuff. So I definitely want to look at this. And then it gives you even further reading, which is pretty cool. So I'll probably have a look at this book instead of Category Theory for Programmers. And then there's this book as well, Programming Language in Foundations in Agda. I mean, I call it a book. It is online, but like online book sort of thing. And this teaches you not category theory per se, but it does teach you maths, but through Agda, and through specifically programming maths. So like lambda calculus is here, which is really good because I want to learn that. Type inference is something that I really want to learn as well. Untyped lambda calculus. And then some de-indentational semantics, which I've heard of, but again, like, I just don't really know what that is. So this would be really cool, and it would teach me Agda. However, I'm probably not going to read this book, because I was also recommended this book, which is Software Foundations, Logical Foundations, which are, it's fairly similar to what this book teaches, but it does it through Coq, or as it's now called, Rock, or Rock, because it's French. I don't know which of these is actually better, but people have told me that this one's better, so I'm going to take their word for it and go with it. In fact, let me just do a quick search here. Agda versus Rock. I don't know how popular Coq actually is, but I think it has good, my 12 years ago, I think it has good tooling apparently. Coq has been designed with theory proving in mind, whereas Agda has been designed with dependency type programming in mind. Okay. They're both easy to install on a Linux system. Agda uses Cabal? Isn't that what Haskell uses? Kaka can bundled, or you can build it from source. Okay. Oh no, is Cabal OCaml or is it Haskell? Doesn't matter. They say Kojo might be easier to learn because it has some existing books that are fairly lengthy and slow-paced. Okay, so Software Foundations is that book. For Agda, it's a bit harsher. Or so Kojo might even be like longer standing. So anyway, I'll probably follow this book instead. And if I finish that book and I feel like I want to read more, there's a sequel. Yep. In fact, there's 7 books in total, but it's the first 2 ones that people generally recommend. So is there a roadmap? I haven't seen this. I don't know if that's for me or for the author, or if it just works at all. By the way, this is Rock Q. Fun story, story, I guess, facts, whatever. It used to be called Coq, but apparently, and because it was French and named after a French guy, but apparently it was crude for English speakers, so they renamed it to Rock, which really annoys me, honestly. Yeah, that just annoys me. They did, it's funny because one of the proposals was to call it Coke, like Coke, and like say that for English you say Coke instead, but then like instead of saying I work on cock and getting harassed, you say I work on Coke, which either means the Coca-Cola company or cocaine. And you know, there's only one other proof-assisted language that also sounds a bit like a drug, and it rhymes with gleam. Glean? Anyway, I want to learn Rock as well. So, I was thinking of learning Agda, but if this book teaches me Rock, I'll learn Rock instead. I only have this open because I want to bookmark it. So there you go. So I'm not going to read that. I'm probably going to start with... I'll probably start with this just because it's so short. I mean, relatively short, and it only, like, if I had started reading this instead of Category 3 for Programmers, I think I'd be up to here, right? Page, like, 70-something? Like, I'd be halfway through. Well, not really, because, like, I think, yeah, halfway through. So, because, like, I was kind of concerned that reading Category 3 for Programmers would take too long. So I read this first, because it's short and it says the basics, so it's probably good to start with the basics. Then I'll read this book. If I want to keep reading, I'll read this book, and in the meantime, I'll be reading Rock along the way. Also this thing, actually. Yeah, see, do I read both of these? I mean, to be fair, it doesn't hurt to read both of these. But, like, these are like lecture notes, right? Yeah, these are lecture notes. So I'll probably read these afterwards. So let me bookmark that and close it. Just in general, NL's pretty good. I'll keep it open for now. I do have a lot of tabs open that I need to address, but things are piling up. Category theory is there. I'll read that first. I'll read this second. This is Software Foundations, Volume 1. Volume 2, I'll just remember to come to later. Rock Q, I'll come to later as well. And this is my recipe. So, without further ado, let's read Basic Category Theory. Now, I was using a PDF editor to take notes, but I no longer want to take notes on PDFs directly. I figured that if I have Obsidian open, I might as well just do it through Obsidian directly and spare myself the annoyance of having to copy everything over. Annoyingly, because like my monitor is so big, but it's also really close to my eyes because my desk is so narrow, which means that on this like recording, I believe the text looks pretty small, but on my screen it looks really big. So I do need to kind of zoom out. Unfortunately, I can't really control it even like more finely, but it doesn't matter too much. And yeah, so this was these are my notes for Category 3 for Programmers. This is how far I got, right? Algebra of types, and yeah, all these notes that I do need to go through at some point. Whew. But yeah, goodbye category theory for programmers for now. Maybe I'll come back to you one day in the future. So we're gonna make a new source note. Call it not that. Call it basic category theory. By who? Tom Leinster. I still need to sort out my keybinds. Tom Leinster. Also, I've been watching The Mentalist. Well, I mean, yeah, more. It's so good. It's so good, dude. I can't get over how good it is. It's different seasons, which is a bit daunting. So, like, I hope it stays good. Otherwise, I will drop it. But, like, so far, it's just such a good thing, dude. I mean, like, it's crazy. Anyway, Tom Leinster published sometime 2014 is all I really know about that. I mean, copyright 2016. It says first published. I could put my the date accessed as well. I'll just say 2014. I mean, this is an archive from 2025, but I believe it hasn't been modified, so I'll put the year 2014. Like, it's crazy how old this stuff is too, you know? I don't think that's gonna save. Nope. How about if I do it here? That's fine, to be honest. Tags is a book. IDs, there's probably some kind of ISBN. There it is. Link to this PDF directly. Any mirrors? I don't know, but if I need to, I can find them. Preview, irrelevant. Right. Let's get started. So, prefix to the RXIV version. Arxiv. Oh, right, like the archive. 2016. Free versions of their books. Freely editable. Cool. Very cool. Like, making educational resources free should definitely be a priority in society. Contents, note to the reader, introduction. Yeah, let's go through. There's no sophisticated text. Okay, in writing it, I've assumed no more mathematical knowledge than might be required from an undergraduate degree at an ordinary British university. I don't do maths, but okay. But I've learned more than I would probably like to. I have not assumed that you are used to learning mathematics by reading a book, rather than attending lectures. Furthermore, the list of topics covered is deliberately short, omitting all but the most fundamental parts of category theory. A further reading section points to suitable follow-on texts. Nice. There are two things that every reader should know about this book. One concerns the examples, and the other is about the exercises. Each new concept is illustrated with a generous supply of examples, but it is not necessary to understand them all. Right. I wonder, yeah, because like if they draw off things that I don't know yet, like topology. In courses I have taught based on earlier versions of this text, probably no student has had the background to understand every example. All that matters is to understand enough examples that you can connect the new concept with mathematics that you already know. Okay, good to know. As for the exercises, I join every other textbook author in exhorting you to do them. Okay, but there is a further important point. In subjects such as number theory and combinatorics, some questions are simple to state but extremely hard to answer. Basic category theory is not like that. To understand the question is very nearly to know the answer. Interesting. In most of the exercises, there's only one possible way to proceed. So if you are stuck on an exercise, a likely remedy is to go back through each term in the question and make sure you understand it in full. Take your time. We're not going to rush through this. Understanding rather than problem solving is the main challenge of learning category theory. I will bookmark this as well, just so I don't lose it. Citations such as MacLean, 1971, refer to the sources listed in further reading. This book developed out of master's level courses taught several times at the University of Glasgow, and before that at the University of Cambridge. I was thinking, by the way, my university does not teach any of this stuff, man. Like, there's nothing like in our courses for computer science about like proof system. I mean, like about like yeah, like proof systems, like theorem solvers. Nothing like that. We do a bit of functional programming, but like we don't get like into any detail like monoids and monads and functors and all that kind of thing. There's nothing that like there's no category theory course even for the math students, so it's very sad. But hey, maybe I can do a master's at some point. Although I think my parents would prefer I get a job. In turn, the Cambridge version was based, mind you, some jobs let you do masters, right? In turn, the Cambridge version was based on Part 3 courses taught for many years by Martin Hyland and Peter Johnstone. Although this text is significantly different from any of their courses, I am conscious that certain exercises, lines of development, and even turns of phrase have persisted through that long evolution. I would like to record my indebtedness to them. Awesome, as well as my thanks to François Petit, my past students, the anonymous reviewers, and the staff of Cambridge University Press. Cambridge, man. Cambridge. I'll go to Cambridge one day, maybe. I wonder if they're good at teaching. I mean, this guy is, right? Category theory takes a bird's eye view of mathematics. So I've read this introduction, like the first like few sentences, and it speaks to me. Category theory takes a bird's eye view of mathematics. From high in the sky, details become invisible, but we can spot patterns that were in. Okay, can we not do that, please? We can solve patterns that were impossible to detect from ground level. How is the lowest common multiple of two numbers like the direct sum of two vector spaces? What do discrete topological spaces, free groups and fields or fractions, have in common? We will be able to discover answers to these and many similar questions, seeing patterns in mathematics that you may have never seen before. Awesome. The most important concept in this book is that of universal property. Right. Look. I was so confused by universal property while reading category theory for programmers. So like, if it can explain it well here, I'll be very happy, because like that seems to be a very important thing. The further you go into mathematics, especially pure mathematics, what's impure, the more universal properties you'll meet. We will spend most of our time studying different manifestations of this concept. Like all branches of mathematics, category theory has its own special vocabulary, which we will meet as we go along. But since the idea of universal property is so important, I will use this introduction to explain it with no jargon at all. Wow. By means of examples. Our first example of a universal property is very simple. Let 1 denote a set with one element. It does not matter what this element is called. Then 1 has the following property. For all sets x, there exists a unique map from x to 1. A unique map. Okay. Is that a rule? In this context, the words map, mapping, and function all mean the same thing. In this context. Map and mapping can mean different things. Indeed, let x be a set. There exists a map x to 1 because we can define a function that goes from x to 1 by taking f of x to be the single element of 1 for each x in the set of x. This is the unique map x to 1 because there is no choice in the matter. Any map from set x to set 1 must send each element of x to the single element of 1. So what I'm questioning is, does there have to be such a morphism? Or, sorry, map. Phrases of the form, there exists a unique such and such satisfying some condition, are common in category theory. Okay. So there exists a unique something satisfying a condition. The phrase means that there is one and only one such and such satisfying the condition. To prove the existence part, we have to show that there is at least one. To prove the uniqueness part, we have to show that there is at most one. In other words, any two such and such satisfying the condition are equal. Right. So, take an example. Take semi-rings, for example. There are multiple semi-rings in set theory that could be considered addition and subtraction, right? The sum and product. But in category theory, there's only one categorical, or like, I don't know, something along those lines. In category theory, there's only one representation of plus and times that fits the whatever requirement the category says. I forgot what it was, but like, I mean, something to do with sometimes and product types. But that unique thing is where addition is disjoint union, and the product would be, I think, intersection. I could be wrong. No, Cartesian product. That's right. So disjoint union is like a union where you join two sets, but you if you have duplicate elements, you include both and tag them. So it's a tagged union, basically, as you would get in programming. And that's why you have sum and product types for set theory. You know, a product type is literally a tuple, right? And likewise, in category, I don't know, in the set category, a product is also the Cartesian product, which, you know, forms tuples, right? If I take two sets, int and string, and then I take the product type of int times string, then that new set will have the Cartesian product of both. So all the possible states will be all the possible combinations, even if they're infinite, whatever, of ints and strings. Whereas the sum type is the disjoint union. So if, let's say, I have int plus int, so they're the same, you know, but I treat each of the numbers from each as like their own unique things. So then I need to tag them, right? I can have my a ints and my b ints, or my a integers and my b integers. So I have a1 and b1, a2, b2, a3, b3, a0, b0, a negative 100, b negative 100, and that's a disjoint union. And that's what we use in programming. We use the category theory specification, I guess, of sum and product. But like, that's what I mean. In category theory, it seems to specifically be a unique property, as opposed to just like a general semi-ring definition, which is, yeah, I mean, multiple things could fit this. Like, we want a specific semi-ring. Speaking of rings, look at that, rings. Properties such as this are called universal because they state how the object being described, in this case the set 1, relates to the entire universe in which it lives, in this case the universe of sets. Okay, so universes is not everything, it's just that particular universe. Why not category of sets? The property begins with the word for all sets X, and therefore says something about the relationship between 1 and every set X, namely that there is a unique map from X to 1. Right. So, my first thought right. So a universal property is one that holds for all what? All objects? Like that satisfies a condition across a set, across a universe. No, it is object. Is one that is a relation between some object and every other object in a universe. For example, it would be a universal property that for all sets X, there exists a unique map from X to the set 1 that only contains one element. So for all sets x, that's kind of language, right? There exists a map from x to 1. So why is it important that it's unique? So I'll add a wonder here. Why is it important that it is unique? Okay, so this is chapter what even? Introduction. This is a table of contents, right? Yeah. Introduction. It's very nice of you to define it so quickly, honestly. Okay, second example. This example involves rings, which in this book are always taken to have a multiplicative identity called 1. Right, so I mean, I did say you're not expected to know all of the examples, right? Similarly, homomorphisms of rings are understood to preserve multiplicative identities. Wait, so do rings not always have a multiplicative identity? I thought that was a requirement. The ring integer has the following property for all rings R. Okay, no, I'll say Z. The ring Z has the following property for all rings R. There exists a unique homomorphism Z to R. To prove existence, let R be a ring. To find a function Z to R. A series of elementary checks confirms that. Hold on. To find a function, is that phi? Phi Z to R, where phi of n, 1 plus however many times of n plus 1, if n is more than 0, 0 if n equals 0, and negative phi of negative n if n is less than 0. Fair enough? Where n is an element of integers. A series of elementary checks confirms that phi is a homomorphism. To prove uniqueness, let R be a ring, and let C Z to R be homomorphism. We will show that C is equal to the homomorphism phi just defined. Since homomorphisms preserve multiplicative identities, C of 1 equals 1. Since homomorphisms preserve addition, okay, for all n greater than 0. Since homomorphisms preserve 0, finally, since blah, blah, blah. Crucially, there can be essentially only one object satisfying a given universal property. Right. Only one object can satisfy essentially. The word essentially means that two objects satisfying the same universal property need not literally be equal. Okay. So that's like up to isomorphism. Only one object can satisfy a given universal property. At least although any two objects can, with the exception of multiple objects, with the exception of objects that are, no, with the exception of, no, unless the other objects are isomorphic to each other. Unless multiple objects are isomorphic to each other. unless there are multiple objects satisfying the universal property that are isomorphic to each other. Right, phrasing. Okay. Let A be a ring with, so this is a lemma now. Let A be a ring with the following property: for all rings R, there exists a unique homomorphism A to R. Then A roughly equals Z. Proof. Let's call a ring with the property initial. Right, initial. We're given, so this is again, like, this is something I heard about but didn't quite understand from category theory with programmers. Probably a bit problematic that I didn't understand it actually. We're given that A is initial, and we proved in example 0.2 that Z is initial. Okay. This proof has very little to do with rings. It really belongs at a higher level of generality. To properly understand this and to convey more fully the idea of universal property, it will help to consider some more complex examples. I might be able to do vector space. Let V be a vector space with a basis V underscored S, where S is an element of big S. For example, if V is finite dimensional, then we might take S equal 1 to n. Okay, I think I understand. So it could be like 3-dimensional, 4-dimensional, 1-dimensional, just anything that isn't infinite. If W is another vector space, we can specify a linear map from V to W simply by saying where the basis elements go. Thus, for any W, there is a natural one-to-one correspondence between linear maps and functions. Indeed there are. This is because any function defined on the basis element extends uniquely to a linear map on V. Uniquely. Let us rephrase this last statement. Define a function I from S to V by I of S equals V sub S. Then V together with I has the following universal property. For all functions f, S to all y, there exists, I think E exclamation mark means there exists one linear f with a bar on top of it. This diagram means that for all vector spaces W and all functions f from S to W, there exists a unique linear map f bar V to W such that f of I equals f, or f bar of I equals f. F bar of I equals f, yeah, okay. The symbol for all means for all, and the symbols there exists only one means there exists a unique, okay. Symbols, plural, cool. I believe I wrote this down somewhere even before, but another way to say, because like I did cover this in maths for my university lecture. Another way to say, or module, another way to say f bar of I equals f is f bar v of s equals f of s for all s. Okay, so the diagram asserts that every function f defined on the basis elements extends uniquely to a linear map f bar defined on the whole of V. In other words, still, the function is bijective. Woo! Okay. Okay. I mean, I got like the idea, but what's the universal property? Given a set, okay, topology. Given a set S, we can build a topological space D of S by equipping S with a discrete topology. All subsets are open. With this topology, any map from S to a space X is continuous. Again, let's rephrase this. To find a function I from S to D of S by I of S equals S. You may feel that this universal property is almost too trivial to mean anything, but if we change the definition of D of S, say from the discrete to the indiscrete topology, in which the only open sets are the null and S, then the property becomes false. It says that all maps out of a discrete space are continuous. Okay? I don't know much about topology. Given vector spaces U, V, and W, a bilinear map F of U cross W, V to Y is a function F that is linear in each variable. Or U cross V, whatever. Lambda. Okay. Some lambda. A good example is a scalar product, dot product, which is a bilinear map. Of real vector spaces. The vector product, cross product, is also bilinear. Right. Like mx plus b kind of linear. Let u and v be vector spaces. It is a fact that there is a universal bilinear map out of u cross v. In other words, there exists a certain vector space T and a certain bilinear map B with the following universal property. Is he making a point with how similar these look to each other? Roughly speaking, this property says that bilinear maps out of U across V correspond one-to-one with linear maps out of T. Even without knowing that such a T and B exist, we can immediately prove that this universal property determines T and B uniquely up to isomorphism. The proof is essentially the same as that of lemma 0.3, but it's more complicated because of more complicated universal property, right? So, in other words, only one object can satisfy a universal property up to isomorphism. I believe. I could be wrong, but that's what I've inferred from all this reading, including this in the other text. Let U and V be vector spaces. Suppose that B, U cross V equal to T. Okay. In the proof that follows, it does not actually matter what bilinear, linear, or even vector space mean. The hard part is getting the logic straight. That done, you should be able to see that there is really only one possible proof. For instance, to use the universality of B, we still have to choose some bilinear map F out of U cross V. There are only two in sight, B, and we use each in appropriate space. Wait. Looks mighty familiar to cross, to product type. Like, compare these two diagrams here. Where's the book gone? These point to T. Indeed they do. Those are the other two T's. And this Y, which here is our T prime, points to the product as it, which is, okay, so that doesn't happen here though. So it's not the exact same, but it does look familiar. Also, these are pointing like this way. Now, J prime of J, T to T, is a linear map satisfying blah blah, but also the identity map is linear and satisfies, okay. What? So then J prime of J is the identity. So by uniqueness part of the universal property, we have J of J equals, yeah. Here we took the F of 0.1 to be B. Similarly, J of J prime equals 1, so J is an isomorphism. Sure. In example 0.6, it was stated that given vector spaces U and V, there exists a pair TB with the universal property of 0.1. Am I misreading this? 0.1? We just proved that there is essentially one such pair, TB. The vector space T is called a tensor product of U and V. Right, tensor product. And written as U tensor product V. Tensor products are very important in algebra. They reduce the study of bilinear maps to the study of linear maps. Since a bilinear map out of UV is really the same thing as a linear map out of that, okay? However, tensor products will not be important in this book. The real lesson for us is that it is safe to speak of the tensor product, not just a tensor product. And the reason for that is lemma 0.7. So the cool thing is, if there exists a unique, for a universal property, if there is just one object, a unique object, as I was saying before, it means that, like, you don't have to arbitrarily choose some model that seems to work. You can literally prove which unique ones should be used for, I guess, like a programming language. And I don't know, like, if it's intentional, but it just so happens that the product types and sum types we have in programming are correct, or like at least match the category theory. I mean, it's probably not a coincidence because there have been like decades upon centuries of mathematical study, but Booleans, or being plus and being times, those also work as a semi-group, but like that specific combination works for the category bool, apparently. Although there are other semi-groups like or semi-rings, sorry, like you could form a complete ring for Boolean algebra if you take plus as XOR and times as AND. But for category theory, it says nope, it's OR and AND, and that's literally what we use, right? It's quite interesting. This is a general point that applies to anything satisfying a universal property. Once you know a universal property of an object, it often does no harm to forget how it was constructed. For instance, if you look through a pile of algebra books, you will find several different ways of constructing the tensor product of two vector spaces. But once you have proved that the tensor product satisfies the universal property, you can forget the construction. The property tells you that all you need to know because it determines the object uniquely up to isomorphism. Sure. Another example, let theta, g to h, be a homomorphism of groups. Associated with theta is a diagram. What the hell is a diagram? So is this like group theory now? Where, what? Turkish I is inclusion of cur theta into g and epsilon? What? The symbol this is often used for inclusions. It is a combination of a subset symbol and an arrow. I do see it, to be fair. But I don't know what that means. They map this into G, okay. Right, and then here is our final example. Take a topological space covered by two open subsets, x equals u union v. The diagram of inclusion maps has a universal property in the world of topological spaces. Inclusions. Well, so like u, the intersection of u and v contains u, or like with some kind of function I, or morphism or map. So it follows for all f and for all g, there exists a unique h from x to all y, to any y basically. So for that means that given y, f and g, such that f of I equals g of j, yeah, there's exactly one continuous map, h from x to y, okay, under favorable conditions, the induced diagram with pi. Van Kampen's theorem. He was working in the 1930s before category theory had been born. By the way, yeah, for those who are unaware, category theory is also very recent, so it's kind of cool. You're now seeing several examples of universal properties. As this book progresses, we will develop different ways of talking about them. Once we have set up the basic vocabulary of different, of categories and functors, we will study adjoint functors, then representable functors and limits. Each of these provides an approach to universal properties. Approach. Okay, what does that mean? And each places the idea in a different light. For instance, examples 0.4 and 0.5 can be most readily be described in terms of adjoint functors. 0.6, representable functors, 0.1, 0.2, 0.8, 0.9 in terms of limits. Well, I think 0.1 was the only one I actually understood. So this is a limit. Sure. Let S be a set. The indiscrete topological space. Okay, sorry. Am I mentioning this example? Imitating 0.5, find a universal property satisfied by the space IS. Is a space whose set of points in S and whose only open subsets of R S itself. Shall I give this a try? That's it, right? So let's take this exercise. I'll open up Pinter. Holy fuzzy search, by the way. I typed paint and it still came up. Okay, we'll get our drawing tool here, give it a test. Doesn't work. Add a new layer, why not? Am I choosing black or what? Pen? Okay, how do I stop selecting? Control D. Okay. And we'll zoom in here a bit. I think Shift, Alt, Control. Oh, there you go. Love the quality there. In fact, I kind of hate it. Let me add a new image here. Fill with white, if you would be so kind. Control V to paste. Quality's awful, isn't it? I guess because it's a certain bit resolution. Control D, that's fine. I don't know where the black border comes from. I wonder if that's my screenshot tool. Oh. Okay. Anyway. So, let's have a look at 0.5. Given a set, we can build a topological space D of S by equipping S with discrete topology. All subsets are open. With this topology, any map. So, I don't know anything about topology, but I'm going to hope or assume that I can still solve this without knowing topology, just because of like the general concept. So, dot ping, unimportant. Okay, so let S be a set. Yeah. The indiscrete topological space IS. Okay, well it's saying that in bold, which doesn't really help me, does it? Because this is discrete. This one is indiscrete. Okay. So let's say we have S to I of S. And this is done via some I. Hold on. But if we change the definition of D of S, say from the discrete to the indiscrete, then the property becomes false. Also, interesting how the universal property is written as a graph here. I guess it doesn't have to be, but it does make things easier, doesn't it? Yeah, I don't know how I'm to solve this, because I don't know anything about discrete topology. Let me just do a quick search. Discrete versus indiscrete topology. Opposite extremes. The discrete topology treats every single subset as open. The indiscrete contains only the empty set and X itself as open sets. What does that mean? So does there exist some map from S to D of S? Maybe. What am I proving exactly? Find a universal property satisfied by this space. So there isn't a function to all X, only to the empty set in S. So when I say that for the empty set, there's a morphism here and here. So for all functions f, let me get the eraser here. Just erase that. Why is my eraser What? Oh, it's erasing like completely. Okay, no. Let me just draw over it. Can I change the? I mean, really, I should have written on a different layer, but no, for next time. Not that I should even be doing this with a bloody thing. So we'll take this dotted line and say that there exists a unique, I don't know if this is correct or not, a unique continuous f. Is this correct? I have no idea, bro. I mean, I don't even know what this means. Okay, I feel like I'm not really meant to do this. Exact exercise. It's like, what the hell? But okay, let's move on. Is this correct? I have no clue. I mean, all I did was change this to that. Like, all I did was just swap these around. Was it before? X. Yeah. Well, discard that. So categories, functors, and natural transformations. 3 in 1. It's crazy. A category is a system of related objects. Great! Wow. See, I didn't know that. I was questioning what the hell is a category actually. I thought it was just like a collection of objects, but then like how do you decide which is which? But yeah, it's related objects. The objects do not live in isolation. There is some notion of map between objects binding them together. I need to piss so bad. Right. So like, a category is a system of related objects. I'm not going to take a note on that just yet. Typical examples of what object might mean are group and topological space, and typical examples of what map might mean are homomorphism and continuous map respectively. Well, that doesn't really help me, does it? We will see many examples, and we will also learn that some categories have a very different flavor from the two just mentioned. So those are actually 2 categories, I guess. In fact, the maps of category theory need not to be anything like maps in the sense that you are most likely to be familiar with. Well, thank God I'm not familiar with anything then. Categories are themselves also mathematical objects, and with that in mind, it is unsurprising that there is a good notion of map between categories. Such maps are called functors. I knew that much. More surprising, perhaps, is the existence of a third level. We can talk about maps between functors, which are called natural transformations. These then are maps between categories. Right. So this is categories, functors, and so a category, a system is that what it said? Holy typos. And a category is itself an object, which means that there exist maps between different categories, and those relations are maps. Okay, which are called functors. And there too are maps between functors, which are called natural transformations. And I'm aware that there are also maps between natural transformations, and I forgot what they're called. What are morphisms between natural transformations? modification, and like it just goes higher and higher basically. Higher order category theory, crazy. In fact, it was a desire to formalize the notion of natural transformation that led to the birth of category theory. Right. So these actually existed before, but they wanted to have something. No, sorry, no, to formalize it. Yeah. By the early 40s, researchers in algebraic topology had started to use the phrase natural transformation, but only in an informal way. That would explain why like the names are not that formal. Two mathematicians, Samuel Eilenberg and Saunders MacLean, saw that a precise definition was needed. But before they could define natural transformation, they had to define functor. And before they could define functor, they had to define category. And so the subject was born. Crazy. Nowadays, the uses of category theory have spread far beyond algebraic topology. Its tentacles extend into most parts of pure mathematics. What is meant by pure mathematics? What is impure mathematics? Right. Right, so there's pure mathematics and applied mathematics, like physics, engineering, and so on, and so forth. Okay. So no, pure mathematics differs from applied mathematics. Let me replace those with in bold. There's a recent part of applied mathematics. Okay, there you go. Perhaps most notably, category theory has become a standard tool in certain parts of computer science. So it has. Applied mathematics is more than just applied differential equations. That's nice to hear, right? It's not just physics, but like even in logic, right? Philosophy. Categories. A category. Holy moly. What is that symbol? Is that an A? Usually people use C. A category A consists of a collection object A of objects. A collection ob A of objects. For each A, B, which are an element of objects, so they're objects, a collection category A, B of maps or arrows or morphisms from A to B. What's that category of? For each A, B, C, there exists, for each A, B, C that are also objects of A, a function morphism B to C times A to B is A to C. Yeah, so G. What does this mean? Like, is this like analogous then? So then, if that's G and that's F, then G of F. Called composition. For each object A, in elements 1 sub A, which of A to A is called the identity on A, satisfying the following axioms. Okay, there are actually some notes here, but even then. Identity laws for each F in the morphism. We have F of the identity equals identity, which equals the identity of F. Yeah. We often write A as an element of category to mean A is an object. Okay, good. For function A to B or A to B, FB, to mean F is an element of the category with A to B. GF means G of F. Fair enough. People also write this as hom sub A, AB. I've seen that yet, or just hom AB. Right, a homomorphism. So then that's just a morphism then. The notation hom stands for homomorphism from one of the earliest examples of a category. Okay. So these are remarks, right? Hold on. I mean, yeah. So I mean, I already knew this. So a category explicitly has objects. For each object, there is a collection of arrows under that. Okay. And then for each ABC, there's composition. For each object A, an element 1A of AA equal identity of A. And there's, sorry, I skipped that. There's also associativity laws. So for each F, so for each morphism from A to B, basically, and each morphism from B to C, and from C to D, you have H of G of F is H of G of F, yeah. For each for each morphism from A to B, we have identity laws. I could have sworn it just said that. Oh no, yeah, no, I read that. For some reason, I just skipped the this one. Okay. So. Categories. So a category, I guess, is defined, or whatever, it consists of objects, morphisms / arrows / maps between those objects. Yeah. Composition of morphisms. Whoops. And for each object, an identity morphism. Denoted by 1 sub A. But not in that font. or maybe so. I don't even know. Can I? Well, no, it's a PDF. Is this typeset, or can I actually like view this source as latex? I'd really appreciate like a latex viewer. It'd make things a lot easier to look at. Yeah. There's probably a source for this somewhere, but what is that symbol? It's A. Show me category. Math Cal. Is that correct? Math Cal A. So that's looking at edit mode. That is not MathCal, definitely not. What is that font, bro? Okay, whatever. I'm gonna use MathCal and change this to C. A category C. So objects which are ob of C. Supposedly is text. Morphisms slash RSS maps between those objects. Denoted as the collection A to B or AB for all, well, for any AB that is in OB, right? Yeah. I'll skip that part and just put the thing directly because I can. Composition of morphisms, such that for any A, B, C in C, category C, where no MathCal, so an A to B and B to C imply the existence of A to C. Is that right? He says times, but whatever. A category must also follow associativity laws. Do I have that even? Yeah, I actually do have that. Associativity laws. Don't know why I felt the need to do it twice. And identity. 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 Okay. The definition of category is set up so that in general from each string A0, A1, AN of maps, it's possible to construct exactly one map, yeah. namely fn minus 1 to f1. If you're given extra information, then we may be able to construct other maps. For instance, if we happen to know that an minus 1 equals a of n, a sub n minus 1 equals a sub n, then f sub n minus 1 blah, 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 is another such map. Yeah? But we are speaking here of the general situation. In the absence of extra information, yeah. For example, a string like this with n equals 4, it's a string, gives rise to maps. But the axioms imply that they are equal. It is safe to omit the brackets and write both as f4, f3, f2, f1. Here it is intended that n is greater or equal to 0. In the case n equals 0, the statement is that for each object a sub 0 of a category, it is possible to construct exactly one map, a sub 0 to a sub 0, so the entity. An entity map can be thought of as a zero-fold composite, in much the same way that the number 1 can be thought of as the product of zero numbers. What? 1 is a product of zero numbers? Is it? I mean, it's the product of itself, I guess, but like, it's weird. Like zero other numbers, I guess. We often speak of commutative diagrams. For instance, given objects and maps in a category, we say that the diagram commutes if g of f equals g of I of h. Okay. Generally, a diagram is said to commute if whenever there are two paths from object x to an object y, the map from x to y obtained by composing along one path is equal to the map obtained by composing along the other. The slightly vague word collection means roughly the same as set, although if you know about such things, it's better to interpret the meaning as class. The term collection can be considered roughly similar to a set, but it is supposedly more similar to a class. If f is the elements a to b, we call a the domain and b the codomain. What? Why is it like talk as if you know things about like strings and stuff, but then explain basic like things from like functions and set theory, like domain and codomain? But okay, every map in every category has a definite domain and a definite codomain. If you believe it makes sense to form the intersection of any arbitrary pair of abstract sets, you should add to the definition of the category the condition that a to b and a, so the intersection of a to b and a prime to b prime equals the empty set unless whatever. What's a definite domain? Well, finite, right? Definite domain versus indefinite. Mixed signs. But that's what matrices. Okay. Right. I'm gonna come back to this. But yeah, so far it seems to require more mathematical like prerequisite knowledge than it lets on. But I'm following along so far, so I guess it's fine. But like that's probably only because I already know some of this stuff. we'll see if I can stick on. Otherwise, I can switch to the other resource, which are the lecture notes. But we'll see. But either way, so far it's definitely like a lot more direct than the other book, Category 3 for Programmers. So that's good. And really, I'm kind of banking on the examples as well to help me also understand things. But I'll probably be mostly relying on the set theory examples. But that's right. Alright then, to be continued.